Welcome back, everybody. Mr. Bremberger.
Miss Agar.
We're going to talk to you guys today about simple circuit measurements. Because we all know how to put these circuits together. However, one of the great aspects about circuits is that we have the ability to measure what goes on inside of them. So it's a nice little combination of science and math, which I'm sure all the math teachers will love. And all of you that aren't good at math probably won't like too much. So to begin, we'll give you a little
Concept math?
yes, thank you. I couldn't find the word. So we're going to talk about, obviously, a little review on the three parts of the circuit. We'll jump in about electrical potential, and then give you a little review on resistance, some background about voltage, and then ultimately we'll sum it all up with some Ohm's law. So we'll start out with those three parts of the circuit. Hopefully we kind of understand these already. Ms. Agar, do you want to talk about these?
Looks kind of a lot like when you're putting together, trying to make a light bulb light up. The last unit. There. Alright, so there are three parts to a circuit. We have the power source, the switch, and the resistor. Your power source in this circuit here is going to be the battery. That's what we've been using here in our classes. Your switch, a lot of you were experimenting a lot with these in the electromagnetic fishing pole contest in the last unit. And then the resistor is going to be what is actually using that electric current. So in this case, a light bulb.
Alright, so one thing we're really concerned about now is this question in the bottom right corner, and that is, what makes the electric current move from one part of the circuit to the other? So that's where we're going to spend at least a little bit of our time on here today. So in order to get a little understanding of that, some terms we really need to understand first, and that is this concept of potential energy. Potential energy is energy that is completely dependent upon the position of something. So, I threw a picture of a roller coaster in here that is right at the top of a hill, the crest of the hill, about ready to kind of roll down to the bottom. Now, that is going to contain a tremendous amount of potential energy. And as that roller coaster plunges toward the bottom, that potential energy will decrease because it's at its maximum. It was at the top of the hill. And electrons kind of behave the same way. And this is what's really responsible for pushing those electrons through the circuit. And this diagram that we have at the bottom right-hand corner that shows these two batteries, I really like a lot because it ties in the idea of differences in charge and kind of why they would want to move from one place to another. But if we're talking about these specific terms and ultimately relating them to our circuit, that potential energy per unit of electric charge is the definition of electrical potential. So if you have a lot of electrical potential at the beginning of your circuit or on one side of it, like we have in this battery, if you have a lot at one side of the circuit and you don't have a whole lot at the other, and that potential difference is great, those electrons are really going to want to speed through that circuit as fast as possible whenever they're allowed to. Because again, we all know that crowded electrons don't really like each other a whole lot. Right? It's like you and your worst enemy. You don't want to sit next to them in class. So these electrons, they're in an entire battery full of their worst enemies, and they don't want to be by them. So if you provide them with an opportunity to move, they're going to take it every time. So here again, we get a little blown up view of that electrical potential. You've got a tremendous amount of potential here on the negative end of the battery, where you have all of these negative electrons stored, and they're going to race to what's attracting them at the other side, which is that positive charge. In batteries in particular, we do this with chemicals. So we'll allow those chemicals to react at one end of the circuit versus the other, which will eventually allow your battery to expire because there's nothing left to react. We'll talk more about batteries later. But what really, again, gets these electrons moving is that difference in potential. Having a lot of electrical potential at the beginning of your circuit and not a lot at the end of it.
Mr. Reed, this kind of reminds me of when we studied cells and talked about osmosis and diffusion. There was a very high concentration of something on one side of a membrane and a very low concentration on the other side. The high concentration wanted to always move with low concentration.
Absolutely.
Similar?
Great point. That's exactly it. And this kind of concept keeps coming up again and again, in science. It's one of those familiar patterns. Lots of movement from high to low, which again, here we have with electrons. So, if we're going to speak specifically about some of the different aspects of the circuit, you can't forget about voltage. Right? Voltage is the difference in electrical potential between those two places. Right? Having a lot of electrons at one end of the circuit and not a lot at the other, that's going to create a big difference in potential, and therefore those electrons are going to want to move a lot faster. I like to liken the voltage to the push behind the electric current. All right, it's a great example would be, your best buddy pushing you from behind. Now, hopefully they don't do this, but if you've got a big, strong, muscular, friend that pushes you from behind, you're going to travel some distance. As opposed to if you have a much smaller, maybe non-muscular friend that tries to push you from behind, or just push you in general. This push is what's forcing those electrons through the circuit. And the greater the voltage, the greater the push behind that current. The voltage sources tend to have two terminals. If you look at a battery, you've got a negative end and a positive end. Those are your two terminals. Also, an increase in voltage will cause an increase in the flow of current. And we'll talk about a equation that's responsible for kind of showing this relationship, in a little bit. But it just makes sense. If you have more things, more push behind current, you're eventually going to have more current in the end. Again, there's our picture of those two batteries again. The electrons ultimately will be racing one another to the end of that circuit until that voltage difference is gone. Now think about this for a second. Maybe pause the video if you'd like. What's going to happen to the battery when the voltage difference is 0? Your battery is going to be dead, essentially. And by the way, when you're looking here at these V's, that stands for voltage. Right? You've got two 1.5 volt batteries here. The D cell battery, the AA battery, they're going to carry the same voltage or the same push behind that charge. Although the amount of charge that's going to exist in those two batteries may be a little bit different. Finally, resistance. This is what's holding back your current. We talked about electrical resistance a little bit, so we should have some idea of what's going on. We obviously have an example of a resistor in the upper right-hand corner. These don't always look like light bulbs or something that you may plug in. Because there are so many circuits that exist within more complex electrical devices, sometimes we have to put these little things in to get in the way of the current, because what might be essential to run part of your electrical device, as far as current is concerned, isn't as vital for the other pieces and could be unsafe for them. So we'll put in these resistors from time to time to kind of dial back that amount of current. The greater the resistance within your circuit, the less current you're going to have for a particular voltage. And you're definitely going to see this when you start putting some of the more complicated circuits together. One battery just might not be enough to light up 4 or 5 light bulbs. And again, that's because we're just not going to have enough current there to overcome all of the resistance that we may have within our circuit. I threw this in here, grade figure 9 out of the textbook. I think it was on page 60 or so. Feel free to check it out. It kind of relates what we're talking about here with electricity to water. So I just threw it in here for a little quick reference. Go check it out if you'd like, or feel free to pause the video. Ohm's law. This is responsible for tying everything together. Resistance equals voltage divided by current. In units, we have ohms, which is your unit of resistance, thanks to George Ohm for finding this. Volts, which is your voltage, and amps is the current, or the unit we're going to use for current. So, a little practice problem for you. Oh, maybe not.
Formulas.
This is these are kind of all the different variations of the formula, and I have a little triangle that I'm going to show you in a little bit that really kind of highlights an easier way of kind of manipulating the formula. Although your science book will refer to current with the variable I, and there's also they'll throw this R out here from time to time for resistance, and in its place use, I believe it's an omega. Yeah. For those of you that aren't up on your Greek alphabet, that's another way of determining, or another way of illustrating resistance. So, practice problem. What is the resistance of a light if the voltage is 9 volts and the current is 3 amps? So,
0.3.
or I'm sorry, yeah, 0.3 amps, exactly. So, if we want to use this this Ohm's law triangle, it's pretty slick. All you really have to do is cover up the part of Ohm's, the part of the equation that you don't know. So if we're looking at our set of information here, the part that we don't know is the resistance. So if we cover up the resistance, and we're using the Ohm's law triangle, we need to divide that voltage by the current. So if you divide 3 volts by 0.3 amps, you're going to get 30 ohms. And it's a pretty slick little way of utilizing or kind of manipulating the formula. So you don't need to memorize formula, just memorize the triangle.
I would definitely write this in your notebook right now.
Absolutely.
Make sure you understand. If you want to solve for resistance, just cover that up. Divide voltage by current. If you want to find voltage, you're going to multiply current by resistance. Pretty slim.
Absolutely. All right, that's all we have for the simple circuit measurements. So, as always, if you have any questions, feel free to see us, or make sure you see one of us. And obviously, one of the things that you need to do in this particular activity is write us a question. So don't forget to do that. Many of you have.
All right, see you soon.
Adios.